So today, functions and relations. So some vocabulary. Now, a relation is defined in math. It's just a way to relate inputs to outputs. That's it. Okay. It's a rule that we use to take input values and generate output values. Okay. That's all it is. Now, normally the way that we write inputs and outputs would be as ordered pairs. You know, the x coordinate represents the input value and the y coordinate represents the output value, right? You've seen that thousands of times, I'm sure. So a set of ordered pairs, if we have a whole bunch of individual ordered pairs, that's an example of a relation. We can show that using set notation. We could represent that conveniently using a t-table. That's a really good way to do it. We could use a graph, or we could use what's called a mapping, and we'll see examples of each of those today. Okay. What do we call the set of all the x values, which more properly, they don't necessarily have to be x values. We may not always use x's and y's, but the set of all inputs is called what? What's the set of all the inputs or x values? What'd you call that? Starts with a D. Domain. There you go, right? That's the domain, isn't it? Okay, the set of all the outputs or the y values usually is called the what? The range. Yep, there you go. Is the range. So we say that a relation that has distinct points, so it's got a set of distinct ordered pairs that would look, if I graphed it like a set of distinct points, we call that a discrete relation, whereas a relation that we would draw by smoothly connecting curves or lines, we call that a continuous relation. Okay, and they look different. We'll see examples of both today. So that's, any questions about what a relation is then? Okay, does that all make sense? A relation is just a way to take input values and connect them to output values, okay, or generate output values. A function is a special type of relation in which each element of the domain is paired with exactly one element of the range. Probably a simpler, more concise way of saying that would be a function is a relation where each input has exactly one output. And I'm sure you're familiar with that idea from previous years. Okay, so here's an example. If we're going to use a set of ordered pairs, here's an example of a set of ordered pairs that represents a function. Okay? Here's an example of a set of ordered pairs that represents a non-function. It's a relation that is not a function. What's the key difference there? And there's literally arrows pointing at it. How come the red set is not a function? Okay, because they're repeated x values. Now, what does that mean? It means an input of 1 pairs to outputs of 9 and 12. So it's disqualified, right? Each input can only pair with a single output, and the input 1 pairs with 2 outputs. So it's not a function, okay? So that's what we would look for in a discrete relation where there's individual points. We look for repeated x values. What do we look for with graphs? Can anybody tell me why this is a function, but that is not a function? How could you easily look at that and immediately tell that's not a function? Okay, I already see people doing this, the vertical line test, right? In order to be a function, a vertical line cannot pass through more than one point in the graph of the relation. And look here, there's multiple places where the graph lines up vertically with itself. And a vertical line intersects the red graph in more than one place. Whereas in the green graph, a vertical line never intersects the graph in more than one place. So it is a function. It passes the vertical line test. Okay. Notice here that we've got different ways of representing some concepts. X and Y are typically the variables we use for input and output. The words input and output go together, right? They're associated with each other, both of those words. Input are the values we're plugging into the function. The outputs are the values that are being spit out. The domain is the set of all the inputs or x's, and the range is the set of all the outputs or y's. How do you keep all that straight? Here's a really simple way. Notice that all of the blue concepts compared to the red concepts are alphabetically, they come up prior to the red ones. If we look at each of these two quantities in alphabetize them. Can't say anything today for some reason. X comes before Y alphabetically, I comes before O, D comes before R, right? Does that make sense? So we know all the stuff that comes first in the alphabet would be grouped together. All the stuff that comes later in the alphabet would be grouped together. And then we can see here, obviously, this is a function because it passes the vertical line test. This is not a function because it fails the vertical line test. We can use the vertical line test not just for continuous graphs like these were, right? These are drawn. I continuously leave my pen on the board to draw these graphs. They can also be used for, the vertical line test can also be used to evaluate discrete graphs of just individual points. Is this a function or not? It's not, is it? If you look carefully, it looks pretty good, pretty good, pretty good, pretty good, not so good, right? At that point right there, we see that there are some points that line up vertically, so this is not a function. Okay, give me 1 to 5 so far. We're going through it quickly. I know that's all review. Is that all making sense? Okay. Okay, so let's explore how if we're given a relation, I want you to be able to come up quickly with the domain associated with that relation, the range associated with that relation, and I want you to be able to tell me, is it a function or not? Okay. So a couple conventions, though, that we got to get straight, because there may be some things, I'm sure you guys all know how to find the domain and the range, but how do you know how to represent them properly? Or do you know that? What's the domain of this first relation? -1, 0, 4, and 6. Okay, so there it is. Okay, notice that in this case, they happen to all be already aligned in numerical order, but when we write down a set of values, the domain or the range, we always want to include the elements in increasing numerical order. So what would the range be in this case? Okay, good. -9 first, -5, -2, and then 3. Okay, thumbs up or down. Is this a function? It is, right? It is a function, isn't it? It is, because notice that each element of the domain only has one element of the range associated with it. It only pairs with one element of the range. So yes, it is. Okay, how about this guy? Now, what's the domain this time? -3, 5, and 8. Yeah, do we list the 5 twice? We do not. That's correct. We do not. There are only 3 separate values that are in the domain, -3, 5, and 8 in order. Now, the range in order would look like that, wouldn't it? There are 4 values in order. Is this a function? No, it's not, is it? It's not, because what's the problem? Yeah, the input value of 5 pairs with 2 output values. Single input, 2 outputs, so not a function. Okay, and again, here's why. Because that and that, right? Oops, don't want to do that yet. I just want to go down a little bit. So how about now here, this is written as a t-table. What's the domain? Where would I find the domain in this table? Okay, good, the x column. Good. All the values in the x column would be the domain. If I put those in order, they just look like that. Agreed? Okay, the range would be all the values in the y column. If I put those in order, there's only 3 of them. Now think carefully about this for a moment. Is that a function or not? Take a second. Is it a function or not? Vote with your thumbs. Okay, it is. It is. So why is it not a problem that I've got these 2 3s? Okay, because they're each associated with their own input, though, right? There's no rule that says we can't have the same output values. We just can't have an input value that produces multiple outputs. I can have outputs that are the same as long as they come from different inputs. See the difference? right? So in other words, you could have repeated values in the range and it's still a function. Repeated values in the domain, no dice. Okay, give me thumbs on that one. Does that all make sense? Okay. What about, so that's we've looked at a couple representations. These are sets because look, we've got set notation there. The script brackets that are enclosing ordered pairs. So that's a set of ordered pairs is one way to show a relation. We can use a t-table. That's another good way. Here's a third really good way, a mapping, okay, where everything in this left blob represents the domain and everything in the right blob represents everything in the set of the range, right? Okay, so then as an example, an input of -2 produces an output of what based on number 5? 3. Everybody agree? So we input a -2, the function outputs a 3, okay? So the domain of this is what then? Okay, and I'll write that as a set, -4, -2, and 5. There's the set that we call the domain. What's the range? Okay, 0, 3, 7, 9. Is this a function? Thumbs up or down? You're right. Sophia, how come? You're exactly right. Okay, 5 has 2 outputs. In a mapping, that's easily seen because there are 2 arrows leaving an input value, right? So this is the reason right here that that is not a function. Okay, how about number 6? We won't write the domain and the range down. Is it a problem that I've got 2 arrows pointing at the same value? No, that's okay because only one arrow is leaving each element of the domain, right? Each input value only has one exit arrow that's mapping to only one output, right? So this is okay. Yes, that is a function. Okay. How about if we look at a graph? That's another way to represent a relation. So here we've got a graph of all the individual ordered pairs. What's the domain, Jimmy, of number 7? Okay, so someone else help us out here. David, what's the domain there? -3, you mean?
Yeah, and then 2. Oh, I didn't see that other.
Okay, good. -3, 0, and 2. And then it looks like there's even, okay, it was kind of getting covered up down there. But there's one, everybody see there's one down there too. Yeah. And that was my bad because I was covering that one up. How could you do that really quickly? How could you see the domain super quickly? Yeah, you're just looking at the x values, aren't you? You're just kind of sweeping across the graph from left to right, and you're just looking at all the x coordinates of each of those points, right? So then how am I going to find the range on this one? Matthew, how am I going to find the range? What is the range? Say it again. The y's. So what are those? What are the y coordinates? Remember, there's one clear down there too. It's 5 actually. So -5. Okay. 1 and 4. Good. Okay. Perfect. In order. And all we're doing is just going from bottom to top, looking at all the y coordinates, right? Is this one a function? Thumbs up or down, everybody. Thumbs down. Okay, good. You see it, right? Because there are 2 points that line up vertically. No, it's not a function. Okay. Now, what about this? So now this is different. All the other examples we've looked at have been discrete relations with just a finite number of individual ordered pairs, right? Whether we look at those, whether we represent those ordered pairs as points on a graph or numbers in a mapping or whatever. Okay, but now we're looking at a continuous graph. So this line is meant to go forever, right? The line goes forever. So what's the domain this time? It's all reals. Everybody see that? because every possible x value is represented on that graph, isn't it? Right? There's no x coordinate that we could ever miss all the way from negative infinity to positive infinity. Agreed? Okay. So the domain is all reals. What's the range? All reals, because all y values are represented, all y coordinates are represented in that graph as well. There are an infinite number of points that we're clumping together to form that line, right? Is this a function, thumbs up or down? Obviously, yeah, it is, right? It passes the vertical line test, so yes. Okay, I'm going to skip ahead. We can skip this stuff. That's not, okay, let's go to this one. Okay, now it gets maybe just a little bit trickier. Okay, what's the domain for number 9? What do you think? Frederic, what's the... we don't care about the angles on this one. What can you tell me about the domain? Okay, it's two lines. Okay, I'm looking for a set of values. Yes, sir. Okay, now am I including -4 or not? I am, right? So the domain, if I write the domain, there's two ways I could write that. I could write the domain as x is greater than or equal to -4. Everybody agree? Or using interval notation, I could write it as, whoops, how, you tell me, how would I write it using interval notation? Comma, infinity. Okay, so how many people are just a little iffy on how to get that? Anybody just not 100% sure how to quickly get that answer? Give me 1 to 5 on getting that answer. Everybody's feeling, okay, that's great. Everybody's feeling pretty good. I'm going to tell you about one way you can always think about this. If we take that graph and we project it onto the x-axis, what would the projection look like? Okay, what do I mean by that? So here's the graph. There's our purple graph. If I project that onto the x-axis, that means I'm going to take each of the infinite points in the purple graph and I'm going to squeeze them vertically. They can't move horizontally, but I'm going to squeeze them vertically down onto the x-axis. Okay. So for example, this point right there is going to get squeezed down to that point right there. This guy right here is going to get squeezed up to right there. What would that projection look like if I projected that purple graph onto the x-axis? Okay, good. It's going to be a ray, isn't it? It's going to be a ray that's going to have a closed endpoint at -4, and it's going to move to the right forever from -4. Everybody agree? So that and that corresponds with our domain, doesn't it? Now, what's the projection of the purple graph onto the y-axis? What do you mean by that? All reals. Okay, so it's going to look like if I project this point, it goes to there. This point stays put, right? And I would graph the entire y-axis. So we could say all reals, or using interval notation, that would be the vertical. Now this is vertical, not horizontal, right? So vertically speaking, what's the positive direction? What is it? Up is positive, down is negative, right? So it's going all the way from negative infinity at the bottom up to positive infinity. That's like the left end point kind of becomes, vertically speaking, the bottom end point. And the right end point is replaced by the top end point, right? We still go negative infinity to infinity though. Okay. So you get the idea of projections. Does that make sense? Okay. Is this a function or not? Thumbs up or down? Thumbs down. It's not, because look, it fails the vertical line test there, doesn't it? Right? If I draw a vertical line, look, that intersects in multiple places. So the answer is no. Okay, what about this ellipse over here? What about the ellipse? What's the domain going to be of that ellipse? Hallie, what do you think? What's the domain? -2 up to, looks like +5. Everybody agree? And if I project that ellipse onto the x-axis, wouldn't that domain just look like it's going to start there and end there? So there is a representation of the domain, right? So using interval notation, I would use brackets because I'm including the endpoints. Agreed? Right? -2 to +5, written as an inequality. X is what? Equal to -2 and less than or equal to +5. Good. Okay, so what about the range? If I project the range onto the y-axis, where is the bottom of that interval? -2 and the top? +4. And I am including those values, aren't I? Right? So as an interval, how would I write that? And +4 bracket. How would I write that using an inequality? Y. There you go. So y, we start with the y. Y is greater than or equal to -2 and less than or equal to 4. Good. Is it a function? No, clearly not. Right? Fails the vertical line test. Oh, it's ho. It's not Christmas time. So.
Red and green last
Yeah, yeah.
All
Oh,
I can see is Christmas.
oh. Okay, I'll try to make better ends. That's
Only do that during Christmas.
there you go. There you go. Okay, so now what about these? So now what if we've got, they're giving us, when are we out of here? Like 35. Okay, so maybe we'll just finish up this page. So number 11, we've got y equals x squared, -x squared plus 3. Okay, so we don't really know how. Yes. You don't have graphs on yours? Oh, okay. Okay. Yeah, so here's, right. So to do this at this point, we don't really know how to graph quadratics yet. We haven't even reviewed how to graph lines yet, right? So this is one where we would rely on a graph. And how would we produce the graph at this point? Desmos or a TI-84, right? So that's where the graphs come from. So we would graph this in the XY plane, and here's what we would get. If we graph this function, notice that it is a parabola, as we'll soon see, right? When we get up to talk about quadratics, graphs of quadratics. It's a parabola with a vertex at the point 0, 3. Okay, how can we do that? Now on Desmos, let's get down to the nitty gritty here, and let's see if we can quickly see how to graph this stuff and find the vertex. It makes it super easy on Desmos. How come it's upside down? Because of the -1 in front of the x squared. You're exactly right, the negative sign. Good.
All I can remember from last year. Yeah. It's like the negatives, numbers affect in front of it, affect how wide or small it is.
You know how vertical, how squished or stretched it is vertically. Yep. Okay, so if we go into Desmos, and all I'd have to do in Desmos, oh man, come on. All I have to do in Desmos here is just graph that. I can graph it with a y even if I want to. So y equals -x squared plus 3, and voila, look what we get. We get that parabola. Now, if I want to know, I need to know the coordinates of that vertex, though, because that is the top x value, agreed? So Desmos is smart. It knows that I'm going to want to know what is the maximum, the highest value on that function. So it gives me a little gray point there. If I click on that, it tells me that it's at the point 0, 3. Okay, that's how you do it on Desmos. How do you do this on your fancy graphing calculator? It's a very good question. I'm going to give you an even better answer. On your fancy graphing calculator, as soon as it pops up here, you do this. Okay, let's clear everything.
I'm guessing you press the graph button.
And I want to do that. There you go. So no, you don't. You have to go to y equals first, and you have to graph that function, or that, we don't know if it's a function, that relation. So we'll go in and we're going to, for y1, we're going to do negative. Remember, if I want to do a negative sign, I'm not subtracting. I just have a negative something. I have to use the negative button, not the minus sign, right? So negative, there's my x, and squared is right there. So negative x squared plus 3. And then to graph this thing, I don't just hit graph. I want to make sure I resize the screen so the graph looks good. So I'm always going to start off by going zoom standard. So hit the zoom button and then 6. So zoom 6, and look what it does. It gives me the same parabola. Now I want to know what that highest point is though. So how do I do that? To find the highest point, I go to the calculate menu for the graph. So I go second calculate, or second F4, and I'm going to choose maximum, right? Because I can see a maximum just means the highest value, right? So I want to find the highest value here. So I'm going to choose 4. I'm going to push 4. And now watch closely here. For the left boundary, I have two options. I could either use the cursor, and I have to tell the calculator the maximum is going to be enclosed between this left boundary and this right boundary. So I have to pick a left boundary and a right boundary that will capture that maximum. So I could just trace to the left a little bit. That's fine. Doesn't have to go very far. Hit enter to tell it, okay, there's my left boundary. Now it's asking me for a right boundary. So I could just trace over to the right of my maximum and hit enter and tell it, okay, well, there's my right boundary. Now this is, I don't know why it wants a guess. So then I have to just pick some value in between and hit enter. And what do you know? It tells me the maximum. Well, look at the coordinates it gives me. This is kind of weird. It gives me the coordinates negative 8.502 e negative 7. What's that telling me? That's telling me it's times 10 to the negative 7. That's a very, very small decimal, right? That's what that means. Now, the calculator is wrong here. It did a numerical calculation, and the actual answer should be 0. But it's pretty close because this is actually negative 0.00000085. So it's really trying to tell me 0. Rounded, it's 0, agreed? But more importantly, the y value is 3. Everybody see that? That's what we need to know, is that y value. And let's pick this up tomorrow and we'll go from there. How about? All right.